All right, hello everyone. My name is Dylan Wong. I am a senior year math major up at the University of Nevada, Reno, and I decided I'd upload some videos to this channel again to uh, just kind of go over some cool and more complex math processes I studied in the last couple years at the university. Some of which, when I got to the higher levels, I felt as though the number of online resources, like condensed, digestible videos, just uh, they weren't very readily available. There weren't very many, there. So I guess I thought I'd kind of go over some topics I feel like I had a pretty good grasp on. One of which is stochastic processes. So I will be beginning a video series first on stochastic processes, which just kind of covers some of the main ones you could use in a practical setting and some of the theory behind how they work. And yeah, so to get right into it, the first one that I wanted to talk about was, discrete time Markov chains. All right, and okay, so what is let's break this down. What is a Markov chain? And I think the easiest way to talk about what a Markov chain is to draw a picture. So there's a kind of graphical representation of Markov chains. So one in which we have several nodes, something like this. So A, B, C, D, right? And these can represent anything really. They're as long as they represent different states in a system. So these can be what restaurant I choose to go to lunch at today. Now, if, say, I had A yesterday, well, then I could go to B, and maybe there's an 80% chance. I like going to B after A. I also could stay at A. However, the same restaurant 2 days in a row, who knows? Probably a little bit lower percent chance that I do that. Something like an 80-20 in this example. And then let's just say from B, I can either decide to go back to A, and maybe I do that half the time. And otherwise, if I had B yesterday, I like to go to D about half the time. And I never get B twice in a row. Lastly, or not lastly, but then let's just say I had D yesterday. Maybe after D, I always want A. So I have a 100% chance of going to A after getting D, if I got D last time. And then C, I'm going to leave this as a little singleton. C is like your favorite restaurant. If you go there once, you're hooked. You can never, you can't bring yourself to go back to any other restaurant. It's just kind of a weird case for convenience of talking about it later. So there's some pretty reasonable questions that may arise from having a system like this. We may want to ask some questions. So first we may define let x sub t equal state at time t, or after, t days of eating out. So I may want to ask questions like, what is the probability of x sub t equaling some value, given that on the first day we had restaurant A, right? That's a pretty reasonable question we may want to ask. Another reasonable question we may want to talk about is that as t approaches infinity, what is p of x of t? Or in this case, p of x of t, given some initial probability, given that we started at A. And you may ask, okay, well, why would we want to know that? But let's think about what this means. After I spend an infinite amount of time or go to an infinite number of restaurants, what's the probability of being at any given one of the 4 available restaurants? That essentially also describes the percentage of time I spent at each restaurant leading up to the infinite number of, visits. So, you could think of this like in your lifetime, how long will you spend at any given restaurant? But let's not get too far ahead of ourselves, okay? So here are some possible questions, basically, that may be kind of reasonable to ask. But for now, I'm going to take those and just set them aside. And I figured it didn't grab that, but that's okay. So let's just set these aside for a second. Oops. Still getting used to this little tool down here. Okay, so with those out of the way now, just kind of forget about those and we'll come back to them. Let us define, if we wanted to answer those questions, right? There's two things we need to do. We should really define some vocab, right? Some general sort of information about the Markov chain. And we should try to communicate this data, these one-to-one relationships, in a more kind of mathematically applicable way. Because right now, I mean, how would we refer to, this probability 0.8 here? I mean, sure, we could call it the probability from A to B or something, involving treating it like a line segment, but that's really a little bit convoluted and it doesn't feel very natural. So where I would like to suggest we go is make something called a transition matrix. And I'm just going to label this big T. So big T equals a matrix, except let's write it as a table first. I feel like that a matrix is just a table, but this will be a little bit more helpful maybe. So let's just say we have all our starting points, right? We can start at state A, B, C, and D, no problem. And from any of these four states, we want to write down the probabilities of going to any other state, A, B, C, and D. All right, so the chance of staying at A, given that you are at A, is 0.2, right? The chance of getting that food twice in a row. The chance of, having A the previous day and then going to B is 0.8. And then if you look, A has no other connections to C and D, so we're just going to put zeros there. Next, if the chance of going from B to A is 0.5, the chance of going from from B to D is 0.5, and then it's 0 everywhere else, right? We never stay at B and we never go to C from B. If we're at C, you'll notice it's 0 everywhere except it can stay at itself, and in fact, it only ever stays at itself. And then D is guaranteed to transfer to A. So from D, you can only go to A. Everything else is 0. Okay, so now one way to check that you did this right is that all the rows should sum to 1. The columns don't need to. They can be anything. But the rows should sum to 1. So, yep, that checks out. 1/2 plus 1/2 is 1, 1, 1. Very good. And that kind of makes logical sense, right? We couldn't have one of these nodes that had a 50% chance of going to D, a 50% chance of going to A, and a 50% chance of going to C. That doesn't quite make sense. So this is what we call the transition matrix, and we tend to write it well in matrix notation. So we could say that the matrix T equals 0.2, 0.5, 0, 1, 0.8, 0, 0, 0, 0, 0, 1. And so this is just a quick transcription of what's in that table to a matrix, because we probably will need to use that. So here we go. We have this transition matrix. And now before we continue going down the mathy route to try to answer these questions that I alluded to earlier, let's first get a little bit of vocab out of the way now that we kind of have an understanding of what a Markov chain is. So I already said these are called states, and now we have a way to classify states. So there's two categories of state. We have transient. So a transient state is one that you visit a finite number of times. Now, in this case, that's a little bit of a relative thing. This is a special case. So if we started anywhere in state A, B, or D, then C is a transient state because we're only going to visit it 0 times, a finite number of times. And then we also have the class of recurrent. So I'm guessing you can all figure out what would fall into recurrent. It's one that we visit an infinite number of times so long as we iterate this Markov chain an infinite number of times. And that would mean that A, B, and D are all transient states, assuming we start in this chain. Now, if we were to start in the chain C, it would be a recurrent state, and these would all be transient because we'd visit them 0 times. But for now, I'm just going to say these are what we care about because we're assuming that we're starting on, one of these 3. Now, the fact that it does matter case by case means, well, you may question, okay, how am I going to know if, there's different kind of cases in which the transient and recurrent states depend on? And that can be simplified down to whether or not the Markov chain entirely is irreducible. Okay, so an irreducible Markov chain would mean like A, B, and D itself. If we just had this would be an irreducible Markov chain. Every link needs to be there. We can't simplify it at all. However, the one we have here, including C, is a reducible Markov chain. And so that's actually because what we have here is 2 separate Markov chains. Anytime you have a node completely disconnected from another one, that would be really best classified as its own Markov chain. However, I wanted to demonstrate the fact that Markov chains are interesting in that you can actually represent multiple Markov chains within one transition matrix, since the zeros in the diagonal and horizontals will basically be the separating line between the two. So if it's reducible, this kind of is subjective. If it's an irreducible matrix, these are fixed. And that's about, I think, all the depth we need to go to for that. Basically, you're welcome to do a little more research, but honestly, it's notation that we don't use too often. So hence why I'm just going to kind of throw that off screen right now. And then one more thing in terms of notation that I do want to talk about is, grab my white pen again, periodicity. So this one, not super important. I'm not going to cover it in great detail. Just I would do a little research, kind of look into it on your own if you want. You can just do a Google and you'll find out periodicity of Markov chains. But it just describes the number of, or rather the frequency with which you can expect to visit a certain node. So in this case, this one would have a period of 1 because every single time it's returning to the state C. So yeah, like I said, I honestly haven't found it too applicable. I rarely used it in all my time going through, upper division math courses at my university. So I don't think I'm going to cover that one very much. Now, let us go back to what we originally proposed, right? Let's try to do an example of this. So we want to solve for the probability of x sub 1 given that, or here, let's do the probability of x sub 1 is equal to a given that x sub 0 is equal to a, right? So let's calculate this. We can look at here and we can say, all right, if we're starting at a, what's the probability that we will be at a next time? Well, that's just 0.2. Very simple. Let's do one more kind of simple case, right? So the probability of x equal 1 equal to c, given that x sub 0 is equal to a. Well, if we're at a, there's no chance we're going to c, so that one would be 0. So that's 2 very simple cases of applying this, right? Now, another reasonable question we may want to ask, though, is just what is the distribution of probabilities after one iteration of the Markov chain, given that x sub 0 equals a? So if we start at a, what are the probabilities of ending up at any of the states is kind of more how this one reads. And for that one, well, essentially we know that we can just take the first column here out of our table, and that's going to be the distributions. Right? Wait, does D? Yeah, D does go to A. Okay. Sorry, I just wanted to check my math real quick. So here we are, and what this actually is sorry, it's not the first column, it'd be the first row. That's where I got thrown off. So this one here would be transition matrix row 1. And that would equal, so if we're going to fill out this vector, we know that if we're starting at A, then the probability of us ending at A is 0.2. The probability of us starting A and ending at B is 0.8, and then it's zeros thereafter. So we've answered this first question. We have found a distribution for A equal, for X after one iteration of the Markov chain when we started at A. Now let's try to take this one further. So let's look at X sub 2, given that X sub 0 equals A. And well, now A, we had two options, right? So this one gets a little more complicated. Because after this first iteration, after at x1, we don't know where we are anymore. There's no explicit, set value. So what we're going to have to do is actually do some matrix multiplication. Now, there's kind of two different approaches here you could go with. And so if you allow me to be a little hand wavy here, what we're going to do is we're going to actually take T, the matrix, we're going to square this whole thing, and then take the first column. Okay, and to do this matrix operation, I'm not going to square out this 4x4 matrix here in front of you guys. I have it pulled up in Symbolab, which is a good tool if you just want a free tool online to do some simple like linear algebra type matrix operations. And we can see that this is the matrix when we square it. Again, I'm doing some hand waving by saying we should square it, and we're going to verify using brute force that this was correct. Now, because we know our initial condition was A, I was saying we take the first row of this matrix, so I have to remember 44, 16, and 40. And, oops, sorry, that's the wrong way. So, come over here, we have 0.44, 0.16, and 0.4. One important thing, a way you can fact check these, is that this should still sum to 1. These should always sum to 1. You should always have a total of 100% probability at being at one of the states. That would mean, if not, you found your way outside of it somehow, which is impossible, and you probably did an operation wrong. Now, let us verify this with brute force. So, how would we get to this with brute force? So we know we have a 0.2% chance of staying at A, meaning if we want to consider the chance that we, after one iteration, stay at A, and then a second iteration stay at A in order to fall into this category, well, that's 0.2 times 0.2. All right, and then, or if we stay at A, we have the 0.2% chance we stay at A, but then we transition to B. Well, there's a 0.2 times 0.8% chance of that happening. Now, consider the alternate case. There's a 0.8% chance that we go straight to B. So we're at B now, and we have two options from there. So while at B, we have a 50% chance to go back to A, meaning there's a 0.8 times a 0.5 chance of going back to A and finishing the end of the two stages there. And there's also the chance that we go to D from A, which is a 0.8% chance to get us to B, times the 0.5% chance that we will then move to D. This is simple. This is like something you should know from stats, like intro to stats. Anytime we want to consider the probability of two events happening, we just multiply their probabilities. And sure enough, if we check this, 0.2 times 0.8 is indeed 16. 0.4 times 0.45 is 0.44, so on and so forth, basically. You can go through and verify these, but indeed, this strategy did work. So while it is a little hand-wavy, we can essentially generalize that P at x sub t is equal to, sorry, given x sub 0 equals some initial condition, let's call it n, is equal to t to the t at row n. So that's kind of the generalized way I'm going to say this. So if you want to know the distribution at any, t time or step in time, then you just have to take the nth row of the matrix, transition matrix raised to the tth power. That is one of the mathematical beauties of writing Markov chains in this matrix form. That just happens to be a consequence of kind of the nature of changing from one state to another. It acts a lot, these operations here and summing these things acts like matrix multiplication. And that's really the kind of data we're encoding when we do that. So now there's one more thing I want to consider, and that is, as I said, what happens as t goes to infinity, right? What happens here? And so we can't exactly take the infinite power or multiply this matrix by itself an infinite number of times. That's not very practical. So we kind of can take a linear algebra approach out of it, and that is, so to find the stationary distribution, that's actually what the name we give this. So the stationary distribution. Which is the sort of the distribution approached after an infinite number of iterations, right? Also, keep in mind that is given some initial condition, right? Some x sub 0. So in this case, let's try to find the stationary distribution for the particular matrix we have here. Well, the way we'd go about that actually is we solve for eigenvectors and the values. So we want to solve for the eigenvectors and values. That is step 1. And again, this is something I'm going to do in Symbolab because I already have the matrix typed up here. I'm not going to work through those by hand, but in vector. So it'll take a second, it'll calculate it, or it'll take quite a while apparently. Maybe I'll just cut to when it feels like finishing. Okay, there we go. It finally finished doing its thing. I forgot. We can't... So, and to do this one, let us use an entirely different Markov chain, okay? So we're going to have a new transition matrix, right? And it's not going to correspond to the above transition matrix. So we have a new T, and we're going to give it something like 0.5, 0.5, 0, and we'll just make it even a 3 by 3 will be fine. Then we have a 0, we have a 1 and a 0, and then maybe we have a 0.2, we have a 0.3, and a 0.5. Something like this, right? That's a valid transition matrix. And let us go plug this into an online calculator once again. So we're going to plug this into Symbolab just for ease of not having to do the eigenvalues and stuff on camera. I'm hoping that you have a basic knowledge of linear algebra / differential equations if you're watching this and kind of getting into stochastic processes, or stochastic, excuse me. If that was something maybe people wanted to see a video on in the future, I could probably cover enough of these topics for you to follow along. But leave a comment if that's the case, letting me know. So let's solve for the eigenvectors. Now, there's going to be a number of them, in this case 2. There's usually 1 minus the number of columns worth, or actually it has a multiplicity. There's 1 for each column, right? And in this case, right, what we're looking for is the maximal eigenvector. Usually it's 1. Normally you get ones with a fraction and stuff. Pretty much always choosing 1 just works, but we're looking for the maximal 1. And if there's negatives, and even if it's a big negative number, you forget it. We're looking for the just not absolute value, just the straight maximum 1. And in this case, pretty simple, right? It worked out that x sub 1 is equal to 1, 1, 1 as our vector. So what this actually means is that if we come here and we were to take this one and write that vector down, right? So at lambda equal to 1, we found that the eigenvector is 1, 1. Actually, I can write this sideways. That's fine. 1, 1, 1. That's our eigenvector. And now all we need to do to get the stationary distribution, right? Step 2 is I'll make a note. We want to choose the maximal lambda. So choose the maximal lambda and the corresponding vector. Then step 2 is normalize this vector. Those, again, you should hopefully know what normalizing is / means, but I'll run you through it real quick. Basically, we need this to sum to 100 while keeping the same proportions that it is. There's a particular formula, but in this case, it's so simple. I'm just going to do it and say that the stationary distribution equals 1/3, 1/3, 1/3. Pretty much the formula is you simply add together everything inside of here and then divide each component by the sum of everything inside. So 1 + 1 + 1 is 3, divide everything by 3. That's how you get the stationary distribution. So what does this tell us? Just as a reminder, this means that in this particular Markov chain, given an infinite number of time passing, we expect to see it spend an equal amount of time basically at all 3 of these, which kind of neat. And so, that's not what it means. After an infinite number of time, we are equally likely to expect it to be at any one of these. Which, again, it does kind of mean the same thing, but it's better if we word it that way, I suppose. And with that, I think that's basically going to wrap up today's episode on discrete Markov chains. There is one more important thing I wanted to say, which is we never quite broke down the whole discrete thing. What does discrete really mean? In discrete, just as a note, right? So I'll just note. As a note, discrete refers to steps include, or just the number of steps rather than periods of time in which steps are distributed. Oops. So, discrete refers to the fact that these jumps, we're just assuming one jump to the other. So anytime we increment this number t here that I was using to represent time, that is, we've assumed it increments the second we jump from one state to another. And that, we kind of have to run through this whole process. Now, in real life, these kind of systems, they're not like that usually. There's not kind of these decision point moments in which you can know with certainty you're transferring from one point to another. In general, when it comes to real life practical applications with Markov chains, we tend to talk more about like over a given amount of time, something will, if we go back to the restaurant analogy, sure, it could be that I'm in this case, it's best modeled by the fact I make it the decision every day to go to one of those restaurants, and it's always at 12 o'clock that I just feel hungry for lunch, right? But it's not always so convenient, right? That on some particular time on the clock I'm just gonna go. In real life, it may work out that I may get busy. I may, stuff may happen. Let's just say every day I have, or between certain hours, I have a given probability within this window, maybe, of going to lunch. And, you know, so I have certain frequencies within there at which, it's likely that I'll go to lunch. And, I'll get more on that next time. But as a little preview, we can imagine over a 1 month period, the number of times that I decide to go out and eat is exponentially distributed. So we could graph the number of times I feel like going out to eat, and it has some distribution that we know. And then now, when we combine this kind of varying randomness with the fact that I randomly am going between the states each time with some given probability, we create this kind of composite, more complex thing. And what's really cool, though, is that despite adding kind of this extra layer of obscene complexity here, it really does not change the core math of how we apply these principles, hardly at all. And so I'll exhibit that through some examples and maybe through some code down the line. But that wraps up today's sort of little mini, not too short briefing on Markov chains. Please leave a like, let me know what you think, and thank you all for watching.